To round off this week, let's look at some examples to illustrate some of the concepts we have seen so far. So we've already seen a function which computes the factors of a number n. So we observed that all the factors must lie between 1 and n. So this is something we can naturally compute using a for loop. So we define factors of n as follows. We assume that the list of factors is empty, and for each number in the range 1 to n, if that number is a divisor, is a factor of n, we append it to the list of factors, and eventually we return this list. So this is a simple function which just takes the list of factors, gives back the list of factors of the input n. So a prime number is one which is divisible by no other number other than 1 and itself. In other words, the only factors of n should be 1 and n if n is a prime. So 17, for example, which is a prime number, has only two factors, 1 and 17. Whereas 18, which is not a prime, has many more factors. It is also 2 times 9 and 3 times 6. So a list of factors of 18 is a longer list than just 1, 18. So this allows us to write a very simple definition of prime based on factors which we've already seen. So a number is prime if the list of factors is exactly 1, n. So what we do is we invoke the function factors and check what it returns and see if it is equal to the list 1, n. So this is another illustration of the fact that if we break up our code into functions, then we can use functions one inside the other and break up our problem into smaller units which are easier to digest and to understand. So here we said that a prime number has only two factors, 1 and itself. We have separately written a way to compute the list of factors, so we can take that list and directly check whether or not a given number is prime. So one small thing to be aware of when we are dealing with prime numbers is that we should not accidentally define 1 to be a prime, because if we just look at this definition that the only factors are 1 and itself, it is a bit ambiguous because 1 is a factor and itself is 1 is also a factor. So we could naively read this as saying that 1 is a prime, but by convention 1 is not a prime. So there should be two factors separately, 1 and itself. Fortunately, if we call our function factors, then factors of 1 will return a singleton list containing the value 1, because it will run from the code will run from 1 to 1, so it will only find it once. Whereas in order for this return statement to be true, I would like the actual value to be 1, 1, n. So n is 1. So fortunately, the way we have written is prime. It will correctly report that 1 is not a prime. But these are the kind of boundary conditions that one must be careful to check when one is writing functions in Python or in any other programming language. So what if we want to list all the prime numbers which lie below a given number n? So we have to just check for every number from 1 to n whether or not it's a prime. So we already know how to check if something is a prime. So once again, we can write a function primes up to, which takes an argument n. So initially we say that there are no primes up to n. Now for all numbers in the range 1 to n plus 1, which means from 1 to up to n, we check if that number I is a prime. Now this is a function we've already written. If it is a prime, then we append it to our list. If not, we go to the next one. And finally, we return the list of primes we have seen. So once again, now we have used a function we have written before, isPrime. isPrime in turn uses a function called factors, which we don't see here. So we have three levels of functions now. Primes up to, which calls isPrime, which calls factors. So this is a very typical way to write nice programs where you break up your work into small functions. Now the other advantage of breaking up your work into small functions is that if you want to optimize or make something more efficient, you might first write a most obvious or naive way to implement a function so that you can check that your overall code does what it's supposed to do. And then you can separately go into each function and then update or optimize it to make it more efficient. So breaking up your code into functions makes it easier to update your code and to maintain it and to change parts of it without affecting the rest. So primes up to n, we knew in advance that we have to check all the numbers from 1 to n, so we could use a for. What if we change our requirement saying that we don't want primes up to n, but we want the first n primes? So now if we want the first n primes, we don't know how many numbers to scan. Right? We don't know where the nth prime will come. If n is small, we might be able to figure out just by looking at it. But if n is large, if we ask the first 1000 primes, it's very difficult to estimate how big the 1000th prime will be. So we have to keep going until we find 1000 primes, and we don't know in advance. So this is a good case for using the other type of loop, namely while. So what we need to do is we need to keep a count of how many primes we have seen. We need to go through all the numbers one at a time to check if they are primes. And we need a list of all the primes we have seen so far. So just to illustrate another point that we have seen, this is a simultaneous assignment which says, okay, initially we have seen 0 primes, so count is 0. We start with the number 1. This is the first number we check whether it's a prime or not. And initially the list of primes is empty. So this says take these 3 values, take 3 C names and assign them these 3 values. Assign, this is saying the same as count is equal to 0, I is equal to 1, and P list is the empty list. So this is the same effect, this particular assignment. Now, so long as we have not seen n primes, okay, while count is less than n, we have to check whether the current I is a prime, and if so, add it. So if the value I we are looking at is a prime, then first of all we have found one more prime. So we increment the value of count, and we have found a prime, so we must add it to the list of primes. Okay. If this is not a prime, we must just go to the next number. In any case, we must go to the next number until we hit a count of n. So we, outside the if, okay, so this is unconditional, we always update. So for each I, we first check if it is a prime. If it is a prime, we update count and we append I to P list. And whether or not it is a prime, we increment I. And each time we increment count, we are making progress towards this while terminating. So remember that it's our job to make sure that this while will eventually get out. This condition will become false. So every time we see a prime, count is going to become count plus 1. We start with count equal to 0. So eventually it is going to cross n. Of course, we are using the implicit fact we know that there are an infinite number of primes. So we will always, for any n, be able to find the first n primes. So when we do find n primes, when we have gone from 0 to n minus 1 and we have reached the count n, we have seen n primes, then we return the list that we have found so far, and this is P list. Okay. So these two examples, the primes up to n and n primes, illustrate the difference between the use of for and while. In primes up to n, we know that we must scan all the numbers from 1 to n, so it's easy to use a for. In n primes, we don't know how many numbers we have to scan to find n primes. So we use a while and we keep count and we wait for the count to cross the number that we are looking for. So it turns out that you don't actually need a for. You can always simulate a for by a while. So let us look at the two typical ways in which we write for. So the first way is this for in a range. So we say for n in the range I to j. So we start at I and we let n go through the sequence I plus 1 up to j minus 1. And for each value of n, we execute this statement, or there may be more statements here. Okay, so this is a block of things inside the loop that we will execute. So if we want to do this without a for, we could do it with a while as follows. So we initialize, so this says that the first value of n is I. And so long as n doesn't cross j, you execute the statement, the exact same statement, and you increment n. So it comes back here and you check now, you get I plus 1, I plus 2, and then when you reach j minus 1, the next time it will be j and it will exit. Right? So we have to have a range in the for. We can just set up a counter and manually increment the counter and check the counter value against the upper bound in the while. The other way that we use for is to iterate through the elements of a list. So n now, if L is a list of values x1, x2 up to xk, n will take each value in this list. So here again, we can now set up positions to walk through the list and pick up the value at each position. Right? So we say we start at the 0th position. And so long as we have not reached the end of the list in terms of positions, we set n to be the value at position I. Then we execute the statement and we increment the position. So both forms of the for can be written as while, but notice that the right hand side is significantly more ugly and complicated than the left hand side. So while we can use the while statement to simulate the for statement, it is much nicer to use the for where it is natural, where we know in advance what exactly we are repeating over. So this makes for more readable code, and in general, more readable code makes for a better program. So what do you need to do to write a good program? Well, first of all, it must do what you expect it to do. So it must be correct. And secondly, it must do it in as efficient a way as possible. We have not looked at efficiency so far. We will look at it as we get further in the course. But we want to do things quickly. We want to do things in the most efficient manner. And this is where the algorithm comes in. How you do something is what the algorithm will tell you. And the second part is that you must write down your instructions in a way that is easy for you to validate as being correct and for somebody else to understand and, if necessary, update. Now, we should not underemphasize this fact of maintenance. You write something today which serves a certain function. Very often, somebody will have to later on either make it more efficient or change the functionality, increase the range of things your program does. And in that case, very often it is not the person who writes the code, but somebody else who has the job of understanding and updating the code. So at every stage, if the person who is making modifications, starting from the person who wrote the code initially, writes it in a clear and readable style, it makes it much easier to maintain the code in a robust manner as it evolves. So to summarize, there are two parts to programming. First is what you want to say, which is the algorithm. And the second part is how you say it, which is the style. So every programming language has a style. Use the style to make for the most effective and readable code you can find. If you have a for, use it. Don't force yourself to use a while, and so on.